Alex. You ready for another example? We want to sketch the graph of g of x equals x to the third divided by x squared minus 1. And I'm just going through the list of guidelines. You need to find all these things that are listed. You don't necessarily have to find them in this particular order. But I'm going to do this order every time because that just matches the guidelines. But the first thing we want to do is find the x-intercepts. And remember, to find x-intercepts, what you should always do is set g of x, or y, equal to 0. So I have 0 is equal x to the third divided by x squared minus 1. To solve this equation, the very first thing I need to do is multiply both sides by the denominator, x squared minus 1, because I don't want to solve for an equation with the variable in the denominator. That simplifies to 0 is equal to x to the third. When I take the cube root of both sides, I get x is equal to 0. So my only x-intercept is at the point 0, 0. To find a y-intercept, I need to do the opposite. I need to let x equal 0. So that would give me y equals, or g of x equals, if you like, 0 to the third over 0 squared minus 1, which gives you 0 divided by negative 1, which is 0. Now you know that if you get 0, 0 for the x-intercept, that also is the y-intercept. But I went ahead and did the work anyway. Now vertical asymptote, remember what you're really doing is you're looking at after the function is simplified. So make sure you simplify first, and then you set the denominator equal to 0. Now this function that you've been given is completely simplified. I can't cancel anything. Please don't cancel x to the third and x squared. You can't because of the minus 1. So all I really need to do is set x squared minus 1 equal to 0. I could factor, or I could add that 1 to the other side. Usually we just add the 1 to the other side, don't we? And you get x is equal to negative 1 and x is equal to positive 1. Those are my vertical asymptotes. But that doesn't tell me the behavior of the function. So if I want to find the behavior of the function at those values, I need to take the limit as x approaches negative 1 from the left, and I need to take the limit as x approaches negative 1 from the right of my function, which of course is x to the third over x squared minus 1. Let's do that before we move on to the positive 1. Okay, now if I plug negative 1 in the numerator, I'm going to get negative 1, but if I plug negative 1 in the denominator, I'm going to get 0. That's the point, right? So what I'm trying to do is I'm trying to figure out if the answer is plus or minus infinity. We already know that much. Now to determine if it's plus or minus infinity, imagine plugging in a number just to the left of negative 1. Now if I plug in a number a little smaller than negative 1, which is just to the left, I'm going to get a negative in the numerator. And in the denominator, when I square a number just to the left of negative 1, like negative 1.01, that's going to square and give me a number bigger than 1, right? And so when I subtract it, I'm going to get a positive. So this is going to give me negative infinity is the behavior. So as x approaches negative 1, my f of x values are going to go down to negative infinity, okay? And we'll see that in the very end when we graph. Now let's look at negative 1 from the right-hand side. So we're talking about a number slightly bigger than negative 1, maybe negative 0.9. Now when I cube negative 0.9, it's still going to be negative. When I take negative 0.9 and plug it in here, it's going to give me a number less than 1. And when I subtract 1 from it, that's going to be negative as well. A negative divided by negative is a positive. So the infinity that I'm looking for is positive infinity. I'm going to do the same thing as we approach positive 1 from the left and positive 1 from the right. I just want to know the behavior of the function. I'm not going to rewrite my function again just for space. But picture plugging in a number slightly less than 1, maybe 0.9. Well, when I cube it, it gives me a positive. But when I square it, 0.9, I get a number less than 1. So when I subtract 1 from it, I get a negative. So negative infinity is the behavior as x goes to 1 from the left side. As x goes to 1 from the right side, I'm plugging in a number slightly bigger than 1. When I cube it, it's positive. A number slightly bigger than 1 squared is a number bigger than 1. Minus 1 is still positive, which is going to give me positive infinity. So this is nice this is going to tell me the behavior, and I'll go back to this page when we graph, so we know we're going up when we should be and going down also when we should be. Now, horizontal asymptotes are the opposite, okay? This is called an infinite limit because our answer is either plus or minus infinity. On the other hand, these guys are called limits and infinity. So what I'm doing to try to find a horizontal asymptote is I'm taking the limit as x goes to infinity of my function, which is x to the third over x squared minus 1. And then I'm also taking the limit as x goes to negative infinity of x to the third over x squared minus 1. Now, in the rule, what you're supposed to do is multiply by 1 over x to the highest power in the denominator. So that's 1 over x squared here, 1 over x squared here. Now, that's going to give me x in the numerator. It's going to give me 1 minus 1 over x squared in the denominator. When I'm taking the limit as x goes to infinity, that goes to 0, which gives me x. But when I plug infinity into that, I get infinity. You know what that means? No horizontal asymptote for that guy. Okay. Over here, I multiply by 1 over x squared. All right. And it's going to give me the same thing. It's going to give me an x in the numerator. 1 over x squared times x squared is 1 minus 1 over x squared of the denominator. That goes to 0, because when you have a constant over infinity, that goes to 0. So that gives me x, but when I plug infinity into that, that's going to give me infinity. You know what? I have no horizontal asymptotes. Because when I took the limit as x goes to infinity or negative infinity, I did not get a real numbered answer. But you know what we do have? We have a slant asymptote. How do I know? Whenever the degree of the numerator up here is 1 higher, there we go, 1 higher than the degree of the denominator. And that's exactly what we have. 3 is 1 more than 2. So what do? Long division. You only need to do this when your degree of your numerator is 1 more than your degree of the denominator. So I divide x squared minus 1 into x to the third, and I go ahead and work all the way down. 0x squared plus 0x plus 1. Ooh, minus 1. There we go. Now what do we multiply x squared by to make it an x to the third? And that's an x, right? And then x times x squared is x to the third. And x times negative 1 is negative x. Make sure you line up like terms. Those cancel. And then here, that gives me negative x minus 1. But since that's negative x to the first, I can't divide by x squared. Now, when I do my division, my answer is x plus my remainder, negative x minus 1. The computer's freaking out. Hold on. Negative x minus 1 divided by x squared minus 1. Y'all, all that matters is this guy right here, your quotient. Don't get hung up on your remainder. All that matters is your quotient. So we have a slant asymptote of y equal x. A lot going on that page. Almost too much, right? But, you know, we covered every bit of this in other sections. So this is kind of a summary. If you're getting hung up on vertical asymptotes, you probably need to go back and watch infinite limits. If you're hung up on horizontal asymptotes, you probably need to go back and watch limits at infinity. Or just come see me, okay? Now it's time to take our first derivative. Now why do you need the first derivative? Because this is going to tell you where your function is increasing, where your function is decreasing, and if you have relative maximums and relative minimums. So let's get started. I have to use the quotient rule. So g primed of x. Remember low d high. So low is x squared minus 1. D high is 3x squared. Minus high, x to the third. D low, 2x over low squared. So x squared minus 1 squared. Now it's time to simplify. If you do have a greatest common factor, you might want to factor it out. Both of these terms have an x, so I could just pull that out. So that would give me g primed of x. X comes out of the numerator, and that's going to leave me with x squared minus 1 times 3x, and then minus 2. You know what? More than x comes out. Let's back up. Let's back up now. Look, that's got an x to the fourth, and that's got an x squared right there. Let's pull out an x squared. Okay, that's going to leave me with x squared minus 1. That 3 is still there. Minus, if I pull out x squared here, I'm still left with, so that 2 of those come out, I'm still left with 2x squared there. Okay, over x squared minus 1 all squared. Now what I want to do next is simplify what's in the bracket. So distribute the 3. So that's 3x squared minus 3 minus 2x squared over x squared minus 1 squared. I continue to simplify. I got that 3x squared minus 2x squared. That gives me x squared minus 3, all divided by x squared minus 1 squared. And I believe, y'all, that's about as simple as that needs to get. Now what I'm trying to do is find critical numbers, right? Critical numbers happen in 2 places, where the derivative is equal to 0 and where the derivative is undefined. Okay? Derivative is equal to 0 when we set the whole derivative equal to 0. So I'm going to say 0 equals x squared times x squared minus 3 divided by x squared minus 1 squared. Now, you've seen this so many times you're tired of watching it, but to solve this, I need to get rid of my denominator because I can't solve an equation with a variable in the denominator. So what happens is those cancel out and I still have 0 on the left. So essentially a fraction is equal to 0 when its numerator is equal to 0, and that's what we're saying in that statement right there. And when I solve this equation, I get 2 solutions right here. It's x equals 0 twice. When I solve this equation, x squared minus 3 equals 0, I get x squared is equal to plus or minus the square root of 3. You're okay with that, right? Now where's this thing undefined? Well, where the denominator is equal to 0, and you know where that is. That says x equals plus or minus 1. Those are our vertical asymptotes. Okay, they don't really count as critical numbers, but they still have to go on our chart because the function is undefined there. So let's do our chart. And it's kind of big because I've got a lot of values I need to take out. Look, we got 0, we got negative square root of 3, positive square root of 3, negative 1, positive 1. So we're starting at negative infinity. Let's do this chart in a different color so we can follow. So we're going from negative infinity to the first number that comes up from the left is negative square root of 3. Then we're going from negative square root of 3 to negative 1. Then we're going from negative 1 to 0. Then 0 to 1. Then 1 to square root of 3. And then finally, square root of 3 to infinity. We've got a really big chart going on here, folks. Lots of intervals. And we need to pick some test values. We're going to plug those into the derivative. I didn't like how high that was. There we go. I need some space to plug that thing into the derivative. And then finally we have a conclusion at the bottom. Now remember, this is the first derivative. So down here I'm trying to decide whether this function is increasing or is it decreasing. Okay? But let's pick some values to plug in, shall we? So negative infinity to negative square root of 3. How about negative 2? That would work. Okay? Now value between negative square root of 3 and negative 1, maybe negative 1.5. There's not a nice whole number in between there, so negative 1.5 would work. A value between negative 1 and 0, how about negative 0.5? And positive 0.5 for the next interval, maybe 2, nope, sorry, 1.5 for that interval, and then 2 would fit in that interval. Wow. Okay, now where are we plugging those in? Into this squared off down here, first derivative. Now look, this denominator is squared, so that is always positive, y'all. This is always right here. That's positive. This right here also always positive. what we're going to have to analyze is this part, the x squared minus 3. That could be positive or negative depending on what we plug in, okay? So when I write this out, I'm going to write my fraction bar. I got the plus from here. Now negative 2 plugged in right here. Negative 2 squared is 4. 4 minus 3 is 1. So that's a positive times a positive divided by a positive, which overall equals a positive, right? So that means I'm increasing on that interval. Now let's do it again. Again, this one's always positive. Here's where we have to do the work. If I take negative 1.5 and square it, okay, first of all, the negative term's positive, and that gives me 2.25. Minus 3 is going to give me a negative number, but the denominator is always positive. Now look, y'all, positive times negative divided by positive is always a negative. Therefore, I'm decreasing on that interval. All right, let's do it again. A value between negative 1 and 0, say negative 0.5. Again, when I square negative 0.5, it's always positive. But when I plug negative 0.5 in here and square it and subtract 3, it's going to be negative. Divided by something squared down here is always positive. Once again, I get a negative, so I'm decreasing on that interval. Plug in 0.5, square it, it's positive. 0.5 squared minus 3 is negative. Right here, always positive. I don't care what I plug in, unless I plug in plus or minus 1, which I'm not allowed to do. Positive. So that's going to give me a negative overall, which is decreasing. All right, plug in 1.5 and I square it, and that's positive. Plug in 1.5 squared right here and subtract 3, that's negative. Denominator is always positive. That's going to give me a negative overall, so I'm decreasing once again. Finally, plug in 2 squared is positive. 2 squared here is 4 minus 3 is positive. 2 squared minus 1 and all squared is positive. All those positives give me a positive overall, so I'm back to increasing. Now let's talk about relative max and relative min. Remember the square root of 3 values? Okay, those are defined, right? Those are critical numbers, real, true critical numbers. And we're going from increasing, let me do this in a different color. We're going from increasing to decreasing. So we have a relative max at negative square root of 3. Now, there's no change along here. Decreasing, 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 decreasing. So we don't have a relative max or min. Negative 1, the function wasn't even defined. Okay, so even if there was a change, that would not be a relative max or min. But at 0, there was a possibility, but there was no change. On the other hand, at square root of 3, we're going from decreasing to increasing. Okay, so that's going to give us a relative minimum at the square root of 3. So we need to make sure we put that on our list. We'll find the y value later, but we do need to find the y values for those. So now we know we're increasing from negative infinity to negative square root of 3, and again from square root of 3 to infinity, and then we're decreasing on all those other intervals. And we have vertical asymptotes at negative 1 and positive 1. And we just have, we don't know what's happening at 0, but it's not a max or a min, right? So we'll find out when we look at the graph. So now we're ready to determine if we have intervals of concave upward, concave downward. Do we have any inflection points? Now, that's going to get fun, right? I wrote the first derivative up here for you. We have to take the derivative of that, okay? How you handle this is up to you. If I leave it like this, you're going to have to use the quotient rule. You're going to have to use the product rule inside the quotient rule and the chain rule inside the quotient rule. You may want to, and I can't tell you if this is going to be better or not, but you could distribute the x squared inside, and that will give you x to the 4th minus 3x squared over x squared minus 1 squared. And that may be easier to take the second derivative. Let's try it that way. Okay? So g double prime of x. Here we go. So low d high. So x squared minus 1 squared times the derivative of the numerator using the power rule, which is 4x to the third minus 6x. Okay? Minus high, which is x to the fourth minus 3x squared, d low. So when I take the derivative of the denominator, use the chain rule. So times 2, rewrite the inside to the first times the derivative of the inside, and all that is over the denominator squared. So now it's going to be raised to the fourth power. Now you'll notice in the numerator, I have greatest common factor going on. I have an x squared minus 1 here, and an x squared minus 1 here. I could pull that out, and that would help some. Maybe it'll help a great deal. Let's see. So g double prime of x is equal to x squared minus 1, just one of them. I'm going to leave one of those inside, which is x squared minus 1, times this 4x to the third minus 6x, okay, minus, now this 2 times this 2x is 4x, and I'm left with x to the fourth minus 3x squared, there, all over this x squared minus 1 to the fourth. Still pretty unattractive. We can see what simplifies. I do know that this x squared minus 1 cancels one of those, and now I have a third in the denominator. What I really have to do to simplify this is I'm going to have to distribute. I could still can't factor out greatest common factors, like, you know, there's an x in common here. I could try to pull that out. That could help. And that's just an x to the first. Or let's just multiply everything out. We can pull that out in a minute. Hold on. G prime of x. Okay, so here we go. X squared times 4x to the third is 4x to the fifth. X squared times negative 6x is negative 6x to the third. Negative 1 times 4x to the third is negative 4x to the third. Negative 1 times negative 6x is plus 6x. I'm going to distribute here. So that's going to give me negative 4x to the fifth plus 12x to the third. And this is all over x squared minus 1 to the third. Now algebraically, where does that leave us? Okay, I got a 4x to the fifth and a minus 4x to the fifth. That's nice. Okay, I've got a minus 6x to the third and a minus 4x to the third, which gives me minus 10x to the third plus 12x to the third is 2x to the third. And then I have a plus 6x over x squared minus 1 to the third. Make that a little bit smaller. Equals. Okay. Now, this is it. It doesn't simplify any further. You could factor out a 2x out of there. And that's going to leave me with x squared plus 3 over x squared minus 1 to the third. Alright, so where are my critical numbers for the second derivative? Okay, remember I need to set that equal to 0. Notice from here, I get x is equal to 0, and from here, I get x is equal to plus or minus the square root of 3. Also, still, if I set the denominator equal to 0, x is equal to plus or minus 1, but those were where our vertical asymptotes are. So when I do my chart, I still need to include those values when I divide up my intervals. Okay? So it looks like the same chart we had before, doesn't it? We're going from negative infinity to negative square root of 3, negative square root of 3 to negative 1, negative 1 to 0, 0 to 1, 1 to square root of 3. Yeah, all that. So let's do a chart. So I'm ready to do a chart. If you'll notice, I erased everything else. I kept our critical numbers at the bottom. Really, our only critical numbers for the second derivative are here. These were vertical asymptotes, so the function was undefined there. I have to include those. And I rewrote the derivative over here so we can find it when we need it. So we're going from negative infinity to negative square root of 3. We're going from negative square root of 3 to negative 1. Negative 1 to 0. 0 to 1. 1 to the square root of 3. And finally, square root of 3 to infinity. So these just happen to be the same values that we had for our first derivative chart. So we have our interval. We'll pick test points for every one of those intervals, and I'm going to pick the same test points I picked the first time. And we're going to plug them in, and we're going to have a conclusion. But this time the conclusion is going to be whether this graph is concave upward or concave downward. And instead of plugging in the first derivative, we're going to substitute into the second derivative. And so values to pick would be, say, -2, -1.5, -0.5, +0.5, 1.5, and +2. And I'm going to plug those into the second derivative, which I have right over here to the right. So when we analyze this, let's think about this. Okay, now what's going to be positive every time is this guy right here, x squared plus 3. No matter what you plug into x and then square it, it's going to be a positive number, and then when you add 3, it's still positive. So every one of these, I'm going to have a plus for that part. But now the 2x is going to depend on what I plug in, and so is the x squared minus 1 to the third. Because when I square a number, if it's bigger than 1 and raise it to the third after we subtract 1, it'll be positive. But if I square a number and it's less than 1, when I subtract 1, it's going to give me a negative, and then when I raise it to the third, it's going to be negative. So we've got to be careful there. So when I plug -2 into 2x, that's going to be a negative. When I plug -2 into x squared plus 3, remember that's always a positive. -2 down here is going to be 4 minus 1 is positive, so when I raise that to the third, it's still positive. And overall, that gives me a negative answer, so I am concave downward on the interval -∞ to -√3. Now when I scoot over here, from -√3 to -1, I'm going to plug in -1.5. Well, 2 times -1.5 is a negative number. Again, the circled one is always positive. I don't care what you plug in. And in the denominator, -1.5 squared, okay, and I subtract 1 from that. So again, -1.5 squared is 2.25. Well, 2.25 minus 1 is positive. To the third is still positive. So what we have here, negative times a positive is a negative, divided by positive is still a negative. So we're still concave downward on that interval. Then when I plug in -0.5, things change. 2 times -0.5 is negative. That didn't change. Positive always for that second factor in the numerator. But -0.5 squared gives me a number less than 1. Subtract 1 gives me a negative. To the third is still negative. So all that simplifies to be a positive. So now I'm concave upward. And then when I plug in 0.5, let's see what happens. 2 times 0.5 is positive. When I plug 0.5 into the circled one, that's always positive. And then 0.5 squared now, that's a number less than 1. Subtract 1 is negative. To the third is negative. So a positive times a positive is positive, divided by negative is a negative. So now we're concave downward there. 1.5 plugged in times 2 is positive. The circled part is always positive. 1.5 squared is 2.25 minus 1 is positive. To the third is positive. So overall, that result is positive, which means we're back to concave upward. Finally, I plug in 2 times 2 is 4, which is positive. 2 squared plus 3 is positive. And 2 squared minus 1 to the third is positive. That's just a big old positive, so I'm concave upward. Now, let's look at where it changed. Notice it changed right here, down to up, which means we would have an inflection point at -1, but remember -1 was undefined. There's a vertical asymptote there. So there is no inflection point here. Here in the middle, we changed from up to down. Now 0 is a true critical number for the second derivative, so this is an inflection point. So at 0, whatever y value that is, you have an inflection point. And remember, an inflection point is just where the graph changes concavity. It's going from concave upward to concave downward. How do we find the y value? Plug it into the original function. Now, if you plug 0 into that, you get 0 to the third divided by -1, so 0, 0 is an inflection point. That was also our x-intercept and our y-intercept. Now look here. We're going from concave downward to concave upward, which would be an inflection point, but remember, it's not defined at 1. So no inflection point there. All right, now see if we can summarize all this information and come up with a graph. All right, so what I've done for you here is summarized all the information that we found. You can go back to your notes and you'll see that we have X-intercept and Y-intercept in the same position at 0, 0. So I'm going to mark that point right there at 0, 0. We have a vertical asymptote at 1 and -1. Look, the original function, remember, was undefined there, so I'm going to do some dashed lines, maybe in red this time. So at -1, we are not allowed to cross that line ever. +1, another vertical asymptote, we are not allowed to cross that line ever, okay? Horizontal asymptote, remember we didn't have one at all. Whenever your degree of your numerator is larger than your degree of your denominator, you don't have one, okay? Slant asymptote, that's a little strange, but we have one at y equals x. So I could do a dashed line to remind myself it's there that goes through y equals x, okay? Now, increasing. Remember, that was our first derivative chart. We were increasing from -infinity to -√3, and then again from √3 to infinity. Check your notes. You'll see that's right. And then we were decreasing on these 4 intervals. Okay? We had a relative maximum. Now, I didn't go and find the y value. We should do that. So we have a relative maximum at -√3, and I plug that into my original function. So it's going to be -√3 to the third divided by -√3 squared minus 1. Now, -√3 to the third, first of all, is negative. Now, √3 times √3 is 3, and there's a leftover √3 up there. In the denominator, -√3 squared is 3 minus 1 is 2. So that's our y value. It won't fit in the parentheses there, but that's where it goes, right there. Now, our y value, when we plug in positive √3, if you'll notice the only difference we're going to have is that the numerator is going to be positive. The denominator is going to be identical for the same reason. So that would be +3 √3 over 2. Now we can find out how big that is so we know where to plot that point. I know you know where √3 is. If you don't, let's plug that in. So 1.73, okay? So negative √3 is about -1.73. Positive √3 about 1.73. Whereas 3 times the square root of 3 divided by 2 gives me 2.598. Let's just say 2.6. Okay, so this is going to be -2.6 here and +2.6 there. So let's plot those points. I was doing that in green, so I'm going to go back to the green. -1.73 and then -2.6. We'll just do the best we can with that, about there. And on the other hand, +1.73. Oh, that point disappeared. Did y'all see that? So -1.73, -2.6. Try to make it bigger. And then +1.73, +2.6. There. Okay. All right. Huh. It keeps disappearing. To make it really big, and maybe it won't disappear. All right. Now, we know we're concave downward from -1 to 0 and concave upward from 1 to infinity. Now, if you go look at your chart, I summarized some stuff like, look at the concave upward. Here we go. I flipped back on you. So notice we're concave upward from -1 to 0. And then there's 2 more intervals. But since √3 is defined in the original function and there was no change, I just wrote it from 1 to infinity. Okay? So when I go back, look, there we are. So -1 to 0 and then 1 to infinity. And I did a similar thing for the concave downward so you can see what's happening there. And then we actually changed concavity at 0, 0. So goodness, let's see if we can use all this information to come up with a graph. Okay, so a slant asymptote means the graph approaches that line. Let's see what's going on here in the bottom left. Okay, so we know we have a relative maximum. This point right here is a high point. And I'm supposed to be approaching this slant asymptote this way. Oh, looks like I crossed it. I didn't mean to. And a slant asymptote this way. Now we could check, are we increasing from negative infinity to negative square root of 3? Look, we are. And then we're decreasing from negative square root of 3 to negative 1. Notice we are. Now on the other side, a very similar thing happens, okay? We're going to have to, these are asymptotes, so our line is approaching those vertical lines. Now, are we decreasing? What's happening from 1 to positive square root of 3? Well, look, right here, 1 to positive square root of 3, it is decreasing. On the other hand, from square root of 3 to infinity, it's increasing. That matches. Okay, what about concavity? Look, we're concave downward. This is concave downward, isn't it? From negative infinity to negative 1. Look, all that's concave downward, just like we have. And we're concave upward from over here, 1 to infinity. Now, what about all the rest of the stuff? What about in the middle? Well, notice it says what's happening between negative 1 and 1. Well, down here, between negative 1 and 0, we're decreasing. So this graph has to be falling. Okay? Well, what about between 0 and 1? Well, it's also decreasing. So it's falling. What about concavity? Does that match? It looks like in my graph, I'm concave upward between negative 1 and 0. Well, look, concave upward between negative 1 and 0. That's what we've got. On the other hand, there's an inflection point, so it changes concavity. It whips around. Now it's concave downward between 0 and 1. All right, and put arrows on the end of there. And there's your graph. Now again, what I would like you to do is take a minute and type that in Desmos where it's a lot cleaner. But I promise you, it will match that graph. And when you find all of this information, you really almost have more information than you need. So you end up using some stuff to graph and then kind of checking it with other things. Like if you focus on increasing and decreasing, the concavity often kind of just matches. All right, so you want to come back for a third one? So come on back to the next video and we'll do one more example.